Hi, I'm Matthew Studley. I'm one of the TAs for the STAT2040DE course, and this is a tutorial on Chapter 5, Random Variables and Discrete Probability Distributions. All of the questions that are covered here can be found in your textbook. I tried to pick questions that didn't have solutions so that you'd have more resources to go off of. I also tried to pick questions that were a little bit more difficult or not necessarily so straightforward so that you have a good kind of process for doing that. And I'm trying to highlight a lot of the things that jump out at me in questions that kind of start leading you down the right path so that you can get the correct answer. With that, the first thing that we're going to have to do is actually determine that we're dealing with a discrete random variable. A lot of the formulas that are going to follow apply only to discrete random variables and distributions, and applying them to continuous random variables and distributions and vice versa are going to get you into trouble. So typically a discrete random variable takes on counted values, so these are whole numbers. Okay, usually do not include decimal places, whereas a continuous random variable is usually something that is measured. It usually takes on real numbers, and these numbers can very easily take on decimal places, where the precision is kind of limited to how good the instrument you're using to measure is. Part A describes a random variable as the number of people requesting vegetarian meals on a flight from New York to London. We could have 0 people, we could have 1 person, 2, 3, 4, but really not any in-betweens there. So this is a counted value, and this is a discrete distribution. Okay. B, the exact thickness in millimeters of a paper towel. So this is something that we would have to measure with a ruler or some other instrument, and we could easily have something that's 1 millimeter, 0.9 millimeters, 0.999 millimeters, and so on. So this is something that's continuous. C, the time it takes a driver to react after the car in front stops suddenly. This is again something that we would have to measure, and depending on the instrument that we used, we could probably get a great deal of decimal places of precision. So this is continuous as well. D, the number of escapees in the next prison breakout. This is a counted value. We could have 1 escapee, 2 escapees, 3 escapees, but not 3.5 escapees. Okay, so this is something that's discrete. E, the length of time that a deep space probe remains in contact with Earth. This is something that we would have to measure, and depending again on the instrument, we could probably get quite a few decimal places of precision. This is continuous. And F, the number of points on a randomly selected buck, where a point is an antler projection at least 1 inch in length from the base to tip. The brow tine and the main beam tip are counted as points regardless of length. Now, I don't really know more than the average person about buck antlers, but it seems like we're counting the number of points, and so this is going to be discrete. Now, they're trying to mislead you here with this 1 inch, making you think that you're measuring something, and in general, stats questions are intentionally trying to mislead you, so be very careful. Read very closely. A lot of these questions really are more reading comprehension than they are any sort of actual math. The next question I've chosen to highlight is question 5.15, and this is a question that has a solution in your textbook. But I thought I would kind of take you through the process of constructing these random variables because it's not always super straightforward. You kind of have a multi-step process, and I thought I would just kind of highlight some of the stuff that's jumping out to me that will lead you down the correct path here. So Zappos is an online retailer that sells shoes for men, women, boys, and girls. An experiment, okay, so where your ears perk up, consists of classifying the next 2 items purchased as either men's, women's, boys, or girls' shoes. Let the random variable x be the number of sales of women's or girls' shoes. Okay, so I really urge you to read these really closely and not kind of just skip to the final punch here. If you read just this sentence alone, it seems straightforward, but you don't really have enough information from the question to figure out what they're talking about. They never talked about any of their sales, but they defined this experiment. Okay, so we're going to take a look at part A, and it wants us to list the outcomes of the sample space. So the way that we do that looks like this, curly braces. And an experiment has two items, and they can be either men's, women's, boys, or girls' shoes. So you can do this very systematically. We could have men's and men's, men's and women's, men's and girls, men's and boys. We could have women's and men's, women's and women's, women's and boys, women's and girls. Okay, now this is a tedious process, obviously. This solution is available in your textbook, but you kind of get how we've gotten to here. If you want to see the full thing, you can check the solutions. But we actually have all the outcomes that we actually need to answer our question for B. So on a test, you would have to do this, but it takes a lot of time. They usually will be smaller sample spaces than this. So what are the possible values for X? Now, if X is the number of sales of women's or girls' shoes in these experiments, then it becomes a little bit more straightforward. Okay, we can either have 0, women's or girls' shoes. We could have 1. Or we could have 2, right? We've got this one here. These two. Okay. And we can't have more than that. We've only got 2 shoes in each experiment. Okay. Now, these are countable, discrete values, no decimal places or anything like that. So X is discrete. The next question we're going to take a look at is question 5.3. And this is very typical of a discrete probability distribution question because you're given the information about this distribution in a table. Okay, so when you have a discrete probability distribution that isn't one of the special distributions we're going to talk about later, this is how the information will be given to you. Okay, they usually don't subscribe to any sort of formula. And you can notice that we're missing a piece of information. Okay, and they're going to ask us to find what the value of, what the probability of X being equal to 5 is. And the one thing that we need to know in order to do this is that all of the probabilities will always add up to 1. Okay, so something has to happen. Right now we don't know the outcome, the probability of this outcome, but realistically we do because we know that this is a complete probability table. Okay, so all of these values must sum to 1. So what we can do to find our little question mark is we can sum all of these values here, and we can subtract them from 1 to get our remainder. And that is going to give us our value of 0.07. Okay. Now, you can probably free up a little bit of space here and put that value right in as we're going to need it. For B, they're going to describe some events, and they're going to want to know what the probability that X takes on certain values here. So here we see X greater than or equal to 2, less than or equal to 6. We can just go straight to our table, and we can identify those values. Is 1 greater than or equal to 2? No, so it's gone. And is 7 less than or equal to 6? No. Okay, all of the other ones satisfy this criteria, so we can just gather them up, add them up together, and get our answer here, which is 0.52. Okay, in a similar way to the way we solved the first question, what we could have done is we could have added up our 0.35 and our 0.03 and subtracted that from 1. That would get us this remainder here, and that might be fewer steps. Okay, there's usually a lot of different angles that you can take on these probability questions, so kind of be mindful of that. It'll help you kind of do them a little bit more quickly with fewer calculator inputs. Okay, but do whatever works for you. Now, our next part of this question is to change this up a little bit. The probability that x is greater than 2, less than or equal to 6. It's very similar to our first equation. So you have to be really careful because these look very similar, but they aren't quite. This value 2 is now no longer included. Okay, so there is a distinction, and you got to pay careful attention because at a first glance these kind of look very similar. We're only going to be taking these values. Okay, what we could have done is we could have taken this 0.52 as well, and we could subtract this 0.2 out because we know that it was included initially. If we want to remove it, we can simply remove it by subtraction. Okay, and that's going to get us 0.32. So lots of different ways to solve these problems. You got to practice them and find what works for you. Okay, I want to find the probability now for C that x is less than 4. Erase some of this stuff. Okay, we can just kind of highlight which values satisfy this criteria. 1 is less than 4, true, keep it. 2 is less than 4, 3 is less than 4, 4 is not less than 4. None of these are less than 4. Okay, so we can add up these guys and get our answer, 0.7. Okay. We can move on to D, find the probability that x takes on the value of 1 or 7. Again, pretty straightforward. We can just go through the table and select the values that satisfy this, 1 or 7, and add them up. Okay, so we've got 1 and 7. The rest of these values aren't included, so we add them, and that gets us 0.38. The next question we're going to take a look at is 5.45. The solutions are available in the textbook for this one, but this kind of combines these discrete distributions along with probability questions. So I know you guys just learned about this, but you don't ever get to forget it in this course. Probability is very important. It's kind of a cornerstone of the course. So this question kind of combines them very well. Agway, a farm and garden supply store, sells winter fertilizer in 50-pound bags. For customers who purchase this product, the probability distribution for the random variable x, the number of bags sold, is given in the table. Suppose a person buying winter fertilizer is randomly selected. Now, this is a very quintessential discrete probability distribution question where they give you this table to describe the distribution and ask you some questions about it. What is the probability that a customer buys more than 2 bags? Okay, so we can just highlight these guys, add them up. The probability that x is greater than 2 is equal to 0.1. Okay. For B, what is the probability that the customer does not buy 2 bags? The probability that x does not equal 2. What we can do is we can take 1 minus the probability that x is equal to 2. Okay, and that's going to give us 0.65. We could also have taken our answer from before and added the probability of x equaling 1 to that, which would give us the same answer. Okay, so a lot of different angles to do this. Sometimes questions will sort of invalidate one or make you solve the problem by equating 2 of them, so keep that in mind. C, find the probability that 2 randomly selected customers each buy 1 bag. This is where our probability is going to, probability kind of equations are going to come back in handy. So we need the probability that x1 equals 1 and x2 equals 1. And since these are randomly selected, we can just multiply the probability of these events. Okay, they're independent because they're randomly selected. And that equals 0.3025. Okay. Now, for D, suppose two customers are randomly selected. What is the probability that the total number of bags purchased will be at least 8? This is going to require us to do the same sort of process for C a number of different times here. Okay, it's going to get very verbose, so I may kind of do a partial solution and get you guys to kind of complete it. First of all, we have to think about how we can make a total of 8 bags between two people. And you're going to realize pretty quickly that if you have one of them with 1 bag, the second person can't possibly buy enough for them to have 8 bags. So these two are going to kind of get removed. And we're going to perform this calculation in C for sets that total at least 8. Okay, so that's 8 or 9 in this case. We can have a person that has, our first person has 3, our second person has 5. Okay, so we could have 3 and 5, we could have 5 and 3, we could have 4 and 4, we can have 4 and 5, 5 and 4, 5 and 5. Okay, and you can fill those in to this equation and add them all up. Okay, so this would be our event. Okay, our sample space is obviously all of the combinations. But what we're going to do is we're going to calculate the probability of each of these individual events using this method here, and we're going to add them all up. So this is going to look something like this. Probability of x1 is equal to 3. Probability of x2 equal to 5. Plus the probability that x1 is equal to 5, x2 is equal to 3. Okay, and you can kind of see where this is going at this point, hopefully. x1 is equal to 4. Okay, and x2 is equal to 4. Okay, and you would continue this on for all of them and add them up. At the end, you should get a value of 0.0023. Okay, so we've taken this probability here where we need 3 and 5, and we've multiplied them. But we can have 3 and 5, or 5 and 3, or 4 and 4. So for every keyword and, we're going to multiply, and for every keyword or, we're going to add, and that should get you to this number. Okay. E is applying what we would call a linear transformation to this distribution. This is something where you got to read closely for the question because it seems like you shouldn't be able to know this. Let the random variable y be the number of pounds sold to a randomly selected customer buying winter fertilizer. Find the probability distribution for y. Now this seems like something that would be continuous, kind of throwing you off. Pounds, something that you would weigh. But if we recall earlier in the question, they mentioned that these are 50-pound bags of fertilizer. So realistically, people are only buying 50 pounds or 100 pounds or 150 and so on. So all we're going to have to do to recreate this probability distribution for y is we're going to kind of recreate this table identically, but we're going to multiply this out. So this is going to be 50, 100 pounds, 150, 200, and 250, right? 1, 2, 3, 4, and 5 bags. And these have the same probabilities, right? You're just describing this variable slightly differently. The underlying phenomenon has not changed. (0.02) and 0.01. Now it's important to note they ask you for the probability distribution for y, so you have to give this table. Okay, this table is a probability distribution. So anytime you're asked for a distribution, make sure you actually report the table. Otherwise, you can kind of get lost figuring out exactly what you have to do. The next concept we're going to cover entails calculating some simple statistics about discrete probability distributions. So this is question 5.62. We get a very typical discrete random variable x and its probability distribution. And in the bottom right, you can see that I've highlighted some equations that are going to be useful to us. All these equations that appear like this can be found in the chapter summary slide in your textbook. If you can look through that and kind of understand all of those formulas, then you're probably okay content-wise, and you may just need to practice using them for any sort of examination. So with that in mind, let's use these equations to find the mean, variance, and standard deviation of x. So sometimes this is also called the expected value, and all you have to do this is to multiply x by its associated probability and perform that for all x's and add them up. Okay. A common mistake that people make is they just add these numbers up and divide by 4 or however many numbers there are. And that is a problem because you're ignoring some of the information that we're given. That would be fine if all of the values in this case for the probabilities were 0.25. Okay, but that's what that kind of average does. It assumes that they appear equally. What we want to do is we want to perform a weighted average, because when we're looking at this distribution, we see that 15 occurs disproportionately often. Okay, so we want to weight our average to kind of take that into account, because this table is a summary table of these values. You could think of these as a stream of values that come out with these probabilities. Okay, so we want to take these probabilities into account when we're calculating the average. So to do that, we're just going to multiply these out. X times the probability of x, that's going to get us 0.5, 1.5, 10.5, 7 plus 3.5, yep, and 1. Okay, and if we total all of these up, we're going to get 13.5, which is our mean. Okay. Now, the next easiest thing to do is to calculate the variance, and we can do that in a similar fashion to the way we usually calculate variance. We're going to take our deviation from the mean, square it, but we're going to weight it again according to the probability. We're going to perform that for every x, and we're going to sum them all up. However, there's kind of an easier way to do that. Okay, so I'm going to try and show you that here. All we need to do is multiply each of these values, these probability values, by instead x squared. So the reason I wrote these out like this is because we can multiply these again by x. Okay, so 0.5 times x is going to get us 2.5. Okay. 10 times 1.5 is going to get us 15. This is going to get us, pull out my calculator here, 157.5, and 20 times 1, obviously just 20. Okay, we're going to add all of these up. 195. Okay, so this is e of x, and this is e of x squared. Okay, and you can make an expected value for any sort of transformation of x. This is the squared version. All we did was multiply x times the probability of x. That gets us this. You could do this with logarithm. You wouldn't need to, but if you ever see that listed, you can perform any transformation as long as you just transform x and multiply it by the probability. Okay, now a much easier formula I find for this is this guy here. The variance of x is also equal to e of x squared minus e of x squared. Okay, so we can subtract the squared mean value from this e of x squared and get our variance. Okay, I find this to be fewer calculator presses. So we do 195 minus 13.5 squared, and that's going to get us 12.75. Okay, so this is our variance. Once we have our variance, all we have to do is just square root that value, and that's going to get us 3.5707. Okay. Now that we know these values, we can answer question B. That's going to kind of take us back to stuff that we were doing, just in the previous two slides. Find the probability that x takes on a value smaller than the mean. So our mean is 13.5. The values that are smaller than that are 5 and 10. And we can just add up the probabilities. 0.1 plus 0.15 is 0.25. Okay. Using the probability distribution, explain why the value of the mean x makes sense. Okay, this kind of touches on what I was talking about earlier. The value of the mean is going to be skewed towards 15 because that is the most frequently occurring number. Okay, so if we look kind of at what went into making our mean, most of the value came from this entry, right? 15 times 0.7 is by far the largest value, so that's going to dominate our mean. Okay, 20 appears very infrequently, so it's actually contributing less to the mean than 10 is. Okay. All right. With that, let's move on. Okay, so 5.68. Suppose the number of rides that a visitor enjoys at Disney World during a day is a random variable with the probability distribution given in the table. We get kind of the classic table that we've been seeing with some new values in it. And this is kind of what a question would look like if it's got some additional flavor here. So now we're modeling the number of rides that somebody enjoys at Disney World in a day. And this is what kind of questions would look like when they're asking you about some sort of plausible real-life event rather than just to do the calculations on a distribution. Okay, so find the mean. Pretty straightforward, right? We're going to take these values, multiply them through. Okay. And so on. So this is going to give us a new line, x times the probability of x. And we're going to sum all of these up. And that will get us a value of 9.04. Okay. Now we're going to create another line in the table, which is x squared times the probability of x. Okay, so we fill this in, 1, and so on. and add that up. And that should get you a value of 84.74. Now our mean is equal to 9.04. We're going to find the variance in the standard deviation. Remember, this formula is equal to e of x squared minus e of x squared. So pay attention that this square is outside the bracket. We're taking this value in the bottom, 84.74, and subtracting the mean squared from this. (9.04) squared. Okay, so instead of having to do this subtraction, we can kind of just multiply through an additional time using values that we already needed to get the mean. And we can get our value of 3.0184. If we square that, then we can get our standard, or sorry, if we square root that, we can get our standard deviation. Which is equal to 1.7374. Okay, now it asks us kind of a question that we haven't seen yet. It says to find the probability that the number of rides for a randomly selected Disney World visitor is within 1 standard deviation of the mean. Okay, so what we're going to do is we're going to take that mean value and we're going to subtract 1 standard deviation, and we're going to add 1 standard deviation to it, and we're going to get a lower bound of 7.3026. And we're going to add the standard deviation to 9.04, and we're going to get 10.7774. Okay, and that's going to get us our range. This is plus and minus 1 standard deviation from the mean. And if we look at the values that actually satisfy this, it's just these 3 here. And we're going to add those up. And that equals 0.62. Okay. Now, D is pretty similar. Find the probability that the number of rides for a randomly selected Disney World visitor is less than 1 standard deviation above the mean. So now we're just doing this portion. X is less than 10.7774. Okay. We're going to take now instead all of these guys. Add up all their probabilities. That's going to be 0.62 that we know is already included, plus 0.09, plus 0.07. Oops. These are 0.09, 0.07, 0.04. And that equals 0.82. Okay. So just walking through these very methodically and remembering that even though we get values with decimals, if it's less than that, our value that qualifies it is a whole number. Okay. This brings me on to an interesting kind of point, is that the mean value for a random variable that is discrete can have decimal values, right? This is a summary statistic. It means that on average, people are riding about 9.04 times a day. Any given day, people are going to ride between 9 and 10. We could see any of these values, but according to these frequencies, we would expect most of the time people to be riding about 9 times a day. Okay, the average person at a park on any given day. The variance, also the same kind of thing. These are summaries. They can contain decimals. Question 5.84 comes from the challenge section for this subsection. And I wanted to go over this question because it's purely conceptual. So the method by which you solve this question is not very straightforward. Suppose x is a discrete random variable with mean, mu, and variance, variance. Let y, a new variable, be defined in terms of x by this equation. Y equals x minus the mean divided by the standard deviation of x. Find the mean, variance, and standard deviation of y. Now, the way that we're going to solve this is to sub in some values of x that we know about to see what they would be transformed to in terms of y. Okay, so the first one we're going to do is we're going to sub the mean of x in for x. So y is equal to the mean of x minus the mean of x divided by the standard deviation of x. Now, a lot of these formulas look very simple because actually this is the act of standardization and it results in very simple outcomes. Okay, so what this is going to tell us is that the mean of x, which will be the mean of y, is going to transform us to a variable, or is going to transform us to a place where y is equal to 0. Okay, so 0 over the standard deviation of x is equal to 0. Now, what this means is that no matter where the mean is for x, this process is going to transform y to have a mean of 0. Okay, so the mu of y is going to be equal to 0. Now, to figure out what happens to the standard deviation of y, we're going to sub in a value that's one standard deviation above our mean for x, and that's going to give us a value for y that's one standard deviation above its mean, which we now know. Okay, so if we do that, we're going to sub in this value plus one standard deviation. And we're going to divide that by a standard deviation. Okay, so we're taking this value that we know about on x, one standard deviation above the mean, subbing that into this equation and getting us a variable, a value for y that is one standard deviation above its mean. And that value is going to be equal to standard deviation of x over standard deviation of x. Okay, that's going to equal 1. Okay, so now we sort of have to do one final step that's pretty inconsequential, but we're going to take our value that's one standard deviation above the mean, subtract it from the mean, and that's going to get us that distance traveled, which is just 1. Okay, that works because these values are 1 and 0, but this is still a step that we should perform. And that's going to show us that our standard deviation of y is equal to 1. If we square that, our variance is just 1 as well. Okay, and that's the act of standardizing something. Puts the mean of the new variable at 0 and the standard deviation of 1. Okay, so you express y in terms of standard deviations away from the mean. Question 5.96 is going to deal with a special type of discrete variable that follows the binomial distribution. Okay, so these are discrete variables that subscribe to a process which causes them to behave in a predictable manner. Okay, and the formula above here is again from your chapter summary, and what's nice about figuring out that a variable follows a binomial distribution is that you get access to a couple formulas that can make your life a lot easier. So if you know that your variable is a binomial variable, you can use this equation to solve for any value. So you can make much larger tables without information that you don't need. But you also can calculate the mean and variance a lot more quickly. You can tell that these formulas don't involve you doing a sum of all the values. Okay, and that can save you a lot of time. So all of these if you had the full table for a binomial distribution, you could do all of these the classic way that we've been doing them. It's just going to be quicker to do them if you recognize that they're binomial distribution. Suppose x follows a binomial distribution with n equals 15 and p equals 0.25. Find the probability that of p of x less than or equal to 2. To do that, we have to first realize that this formula up here only works for a single value of x. So if we want to find the probability of a more complex event, we're going to have to combine some simple events. So we can find any of these individual probabilities for single values, right? Since they're discrete, this is a non-infinite number. We could not do this for a continuous distribution. And we can go through this. Now, we can easily find, using the formula, this value by subbing it into this equation. Okay, we've got 15, choose 0. Okay, and on your calculator, this operation probably can be done using a button that looks like this, NCR, sometimes it's NCK. Okay, but you're looking for this. It's usually a button that you have to push Shift to get access to. So make sure you know where this is because you will need it. And if it's written like this, you would say this 15 choose 0, you would write 15 C0 on your calculator. Okay. We'll take our probability, 0.25 to the power of 0, and multiply it by 1 minus 0.25, 0.75 to the power of 15. Okay. Now, this is just a formula that implements classic probability for you. We have no successes and 15 failures. We need all of those events to occur simultaneously, and this choose operation covers the number of different ways that those events can occur. So we can perform this for all of the other ones as well that we listed. This time we've got 1 success, and now we have 1 fewer failure than before. 2 successes. Which of those will be successes? The 2 successes, and the now 13 failures. So you can plug these into your calculator, and you will get these values: 1.336, 0.0668, 0.1559. If you add them all up, we can get these values here, just like we kind of initially indicated. And our probability that x is less than 2 is equal to this. Less than or equal to 2. Now, if they say less than 2, that means just 0 and 1. 2 is no longer included, so we can use a lot of the same information here that we just calculated, which is good. Try not to do more work than you have to. And this is just going to equal 0.0802. Okay. this value I gave wrong. This should be a 0 here. 0, 1, 3, 3, 6. Reported more decimal places than I meant to, but that's fine. And this now makes more sense. Again, now, if we're just calculating for a single value, we just plug this right into the formula. Probability that x equals 7 is equal to 15, choose 7, times 0.25 to the power of 7, those 7 successes, 0.75, the remaining number of failures, and we can just put that in the calculator and get the value 0.0393. Okay, here is where stuff gets a little bit tricky, but not necessarily much more. It actually gets easier because now we're going to start talking about how you can compute these in R. Now, you could probably be looking at this and think to yourself, oh no, I have to calculate 7, 8, 9, 10, 11, 12, all the way up to 15 and do this process by hand, and it would be very tedious. And you'd be absolutely correct. You definitely don't want to do this. A faster way to do this would be to do 0, 1, 2, 3, 4, 5, 6 and subtract that from 1. Right? Probability of 0, 1, 2, 3, 4, 5, 6. Just like this above here, and subtract that from 1. That would be slightly faster. But we are going to actually use an R command called pbinom. Okay. Now, the problem with this command is that it only gives us x less than or equal to whichever value we put in. Okay. So we can easily get around that by just doing 1 minus, putting in 6, because we want greater than 6, so we want less than or equal to be 6 on the other side, and we'll subtract that from 1. So we've got 6, 15, and our probability. Okay, so this is the structure of this command. And the probability that x is greater than 6 is equal to 0.0566. Okay. And this makes sense. You succeed about a quarter of the time. So to get more than 6 successes is probably a very rare event. Something like 15, 14, 13 successes are going to be all very, 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 very low numbers. Okay, so it's good to keep in mind that these make sense. Now, this is slightly different. We have greater than or equal to 6. So in order to do that now, we have to do something similar. We can use the same command, but we have to be a little bit clever. Now, we're going to subtract from 5. Okay, the p-binom of 5, that's going to give us 5, 4, 3, 2, 1, which is the complement of this event. So we'll subtract that from 1. Okay. And there we go. Now, we've got a range here for f. And so we're going to have to be a little bit clever. P-binom, remember, always gives us less than or equal to this value that we put in. Okay, so we're going to first calculate the probability. Actually, maybe I can list this more formally so that it's easier to follow this along. We could find this by taking the probability that x is less than or equal to 10 and subtracting the probability that x is less than or equal to 2. Okay, so if it's less than or equal to 2, that will be the kind of lower tail that's not included in this x greater than or equal to 3. Okay, so what we're doing is we're taking all of the values that are less than 10, and then we're removing the values on the low end that we don't want from that. Okay, so less than or equal to 10 is fine. That's exactly what we wanted. Unfortunately, that gives us everything all the way down to 0, and we just want up until 3. So we're going to take everything below it and remove it, and that's going to look like this. And the reason I structured it like this is because that's the format of this p-binom command. And so we're going to do 10, 15, and our 0.25 parameter of the distribution, and we're going to subtract this command here, which is going to get that remainder on the lower end that's not included in our interval. We're going to put 2, 15, and 0.25. So this is something that you should definitely read the documentation of in R, so that you're really familiar with using these commands, because it'll save you a lot of time. It's going to be really good for the assignments because you're allowed to use R, and so that'll just kind of speed everything up. The result that you should see is 7638. Okay. You can modify this command to provide the right side of the value. So you could implement something called, or you could put a flag on lower.tail and have that equal to false, and that will give you the right side of this distribution, non-inclusive to the value. But it's much easier, I find, to just use it this way. This is going to give you everything less than or equal to 10. Okay, and then since we want 3 to be included, we're going to say less than or equal to 2 on that end. Okay, because this is kind of, since we're subtracting it, that's the part that we do not want included. Okay, that will be included in everything less than 10. So this definitely uses a little bit of practice, but I've got a couple questions that are going to use this sort of information. So this question here is a binomial distribution in action. So this is described in a way where you have to determine that this is a binomial experiment such that you can apply the formulas and the commands that you have access to. This doesn't jump out and say, I'm a binomial distribution, plug in these values. You have to read and figure out that these things qualify to be binomial experiments, and you use that knowledge in order to save yourself some time in kind of calculating this. In addition, there's kind of no other way to do this question. So here's some of the stuff that you're looking for. So 5.104, the battery manufacturer Varda sells a car battery with 800 cold cranking amps and advertises great performance even in bitterly cold weather. Varda claims that after sitting on a frozen Minnesota lake for 10 days at temperatures below 32 degrees Fahrenheit, this battery will still have enough power to start a car. Suppose the actual probability of starting a car following this experiment is 0.75, and 15 randomly selected cars equipped with this battery are subject to these grueling conditions. So the first thing we're looking for is n identical trials, so a fixed number of trials, and we have that right here with 15 selected cars. Okay. Each trial can result in only a success or a failure. So these cars can either start or not start, and we know the probability that this will happen. Okay. So this is our P here, and this is our N. Trials are independent. These cars are randomly selected. They shouldn't impact each other in any way. The probability of success is constant from trial to trial. We kind of already touched on this. The probability is 0.75. Okay, and we're going to look at how we can now apply the binomial distribution because we've met all 4 of these criteria. The first question asks, find the probability that fewer than 10 cars will start. So this is the probability that x is less than 10. We can write this another way. We can write this the probability that x is less than or equal to 9. And that's a way that we can directly put that into our p-binom command in R. 9, 15, and 0.75. We put our parameters in, and we get our answer. 0.1484. Okay. Next on B, find the probability that more than 12 cars will start. This is the probability that x is greater than 12. And we can write this as 1 minus the probability of x less than or equal to 12. Okay, remember we're phrasing it in this less than or equal to format because that's how it's easiest to go into our p-binomial command without making any mistakes. Right, 12, 15, and 0.75. And that is equal to 0.2361. Okay. So C, I included this question additionally because this pops up a couple of times in your textbook and they don't really have any rhyme or reason for how to answer this, and I'm not sure you guys are actually equipped with the tools to deal with this question yet. This kind of touches on hypothesis testing, which is going to come kind of a lot further along in the course. But what we're looking to do is we're looking to take an event that allegedly occurs and assess whether or not we believe the parameters of this binomial distribution because of its rarity. So if we think that these cars start approximately 75% of the time, and we are able to sample an experiment very easily where all 15 of them start, then we would be a little bit skeptical about this probability and kind of say like something about this experiment is not quite right. We might not have the correct information. So there's a couple things that you guys need to know in order to do these correctly. First of all, when they say suppose 9 cars actually start, what we're actually going to be considering is 9 or a more extreme value. And by extreme, we mean further away from the mean. Okay, so in order to find the mean, we take n times p for a binomial distribution. This is one of the nice things about figuring out that something is a binomial distribution. You don't have to do the classic discrete probability distribution mean calculations, and that gets us 11.25. So in this case, 9 is less than 11.25, so we want 9 or fewer cars. And that's what we're going to adjust. The second thing that you guys need to know is that we're going to be comparing this to a probability of 0.05. Okay, and this is just a general cutoff. Whenever you're not given a probability to compare it to, you can just assume that you would be comparing this to 0.05. What we're kind of saying here is that if you sample something randomly and you get a value that should occur less than 5% of the time, you can be skeptical about it. Okay, so that's the way you'd interpret that. So what we want to do is we want to test if the probability that x is less than or equal to 9, and we want to compare that value to 0.05. Okay, so we're going to put this in our p-binom command. Oops. 9, 15.75. And that is going to get us a value of 0.1483. Okay, and so we can kind of say that this event that occurred would occur 14% of the time. And since this is this is greater than 0.05, there's nothing to suggest that our information is wrong. Okay, we wouldn't be suspicious about any of this, any of these values, this p-value. Okay. However, if we saw something like a value of 14 cars, then since 14 is higher than this mean, we would do 1 minus p-binom for 14. This would actually give us the value for 15 cars. So sorry, I said that incorrectly. Okay, and this is not for question C. This is just assuming you had a value that was above the mean. You would have to find everything, the probability of 15 or greater, which is just going to be 15. Okay, so we do this as 14, subtract that from 1, and that's going to get us 0.0137. And that's something that we would expect to happen about 1% of the time. So if we sample that value, then we could be a little bit suspicious about that p is equal to 0.75. Okay? The next 3 slides are going to each deal with a special discrete distribution that comes up pretty frequently, so it's good to know them. And some of these have a pretty similar layout to the binomial distribution, so it's important to not get confused. So I'll try and touch on a lot of the stuff that you're looking for to classify these correctly so you can use the right formulas and get the right answer. The first one we're going to talk about is the geometric distribution. And you can see the formulas at the top. 5.138, according to the Anxiety and Depression Association of America, approximately 8.7% of all adults suffer from a specific phobia, such as high bridges or old elevators. An experiment consists of selecting adults at random and asking them if they suffer from any kind of phobia. So at this point, they could set this question up to ask you questions that would subscribe to a binomial distribution. But when we take a look at part A, what is the probability that the 5th adult selected will be the first with a specific phobia? This is really the keyword that you're looking for that will indicate that you're dealing with a geometric distribution. In general, you sample individuals until you get your first success. So the experiment will always proceed failure, 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 success, and then it will end. Whereas with a binomial distribution, you have a set number of n, regardless of how many failures or successes you get. Okay, so that's kind of the difference here. We've got our p, and we're going to write that as a probability. And we can just plug some values into this formula up there. And you can see that this is really just constructed exactly the way you would calculate this probability of 4 failures and a success. Okay, so we need failure and a 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 success. Okay, so this just kind of makes it a little bit easier to use the formula, but realistically, all of the rules for probability still apply. And if we plug this into a calculator, we get this answer. Now we can also do this with software. This isn't particularly difficult to do by hand, so I usually wouldn't cover it, but the software commands for R operate on slightly different input values. So I just want to make that, kind of get that out in the open and make that very clear. So the command that you would use would be dghome. And the reason we're going to use the D version of this command as opposed to the P version of this command is because we're just using it for a single value, just x equals 5. So if we wanted a single value, we would use D. Whereas in some of the questions coming up later, we're going to be asked about ranges or intervals, and for that we're going to have to use the cumulative distribution, which is going to be the P version of that command. So those apply to all of the other commands that you'll see here. And it's a really good idea to go and read the R documentation. I know I've been saying that a lot. Now, the reason that I'm bringing this up is because if you read the documentation, you'll know that R takes the argument here as the number of failures. So it is kind of understood that the final event is a success, and then the experiment will stop. So instead of plugging kind of 5 into our equation like we do here, we actually need to keep track of the number of failures. Okay, and that makes it a little bit confusing sometimes, but it's just something that you have to keep track of, and it will become pretty natural. So this will obviously give you the same answer. Maybe with even more decimal places than you would want. Let's move on to B. What is the probability that at least 8 adults will be selected before identifying a person with a specific phobia? So what this means is we have 8 adults equals 7 failures, 1 success. Okay, that's the way that they seem to lay it out in the textbook. Okay, so the way we would write this for our formulas would be that we would be looking at x greater than or equal to 8. Okay, and if we were going to do this for the failures, this would be x is greater than or equal to 7 failures. Okay. Now, we can't do this with the formula because presumably this could go up to infinity, so we actually can't sum all of these values, and that's where we're going to use software. So this is equal to the probability of x less than or equal to 7. Okay, but this is 7 total events, total selection, not the number of failures. So when we go and put this into our R command, we're going to now do pgeom because we want this range. And we're going to put 6 in here. Okay, so 6 failures. Because this is the area that's not included, we want 7 or more failures based on this question. And we're going to put our probability in. And that will get us 0.5288. Okay. C, what is the mean number of adults who must be selected before identifying a person with a specific phobia? So if we kind of just repeated this experiment over and over again, what would the average or expected value be? This is where these commands come in. These formulas come in handy. This is pretty simple. And this is equal to 11.4943. So on average, we would expect to have to sample, around 11.5 people. Sometimes more, sometimes less, but this is the kind of range that we would expect to sample, ending on our first success. Now, this kind of question, the textbook seems to like this style. I don't know if you really have the tools, again, like I said, to deal with it, but we know that 35 is significantly greater than 11.4943. And so we are going to calculate the probability that x is greater than or equal to 35. Okay, so again, this is really similar to this here. If we have 35 people sampled, that means we have 34 failures, so we need greater than or equal to 34 failures. And when we write this, greater than or equal to less than or equal to 34, right? So this is a framework where you can easily put it into R. But we remember that we're dealing with the total number of failures. So we have to reduce this by 1. $33 and our probability. And we get this value. Okay, and we're going to compare that to that 5% rule. And this would obviously be based on these results. This is less than 0.05. we would say that this is a very unlikely occurrence. It's possible that this 8.7% value may not be valid. It's possible we might be selecting from a group of individuals that don't follow this 8.7% information that we have access to. Okay, something along those lines. The next special discrete distribution that we're going to talk about is the hypergeometric distribution. It's pretty similar to the binomial and geometric distributions in that it deals with the idea of successes and failures. However, in this particular event, the probability is no longer fixed because as individuals or objects are sampled, the probability changes. They're not replaced back into the population. And this usually occurs when the population and the sample are small enough that it causes removal of individuals to change the probabilities very substantially. So generally, you're going to look out for words like without replacement, or you're going to just kind of keep an eye out for a situation that describes that phenomenon instead of just calling it as such. In 5.144, says in January 2018, a blue moon combined with a lunar eclipse as the moon was at its closest point to Earth, creating a super blue blood moon. The best place in the United States to see this celestial event was in the West. Suppose that in a group of 25 people who work in the same Palo Alto, California office, 15 actually saw the super blue blood moon. 5 people from this group are selected at random. Okay, so we've got a couple pieces of information. Again, we're dealing with pretty small numbers. So this is our population of people that we're sampling from. We're going to draw a sample size of n, and we're keeping track of who's seen this blood moon. There's 15 of them. This is going to be our big M. Okay, so we can just plug some of these values into our formula for x equals 0, and we can get the answer to A, the probability that none of the 5 people saw the super blood moon. Super blue blood moon. Kind of a mouthful. All right. We're going to take 15, choose 0. Multiply that by 10, choose 5. Divide that by 25, choose 5. And that gets us an answer of 0.0047. Okay, pretty simple. What is the probability that at least 4 people saw the super blue blood moon? So that's the probability that x is greater than or equal to 4. And that's the probability that x is equal to 4 plus the probability that x is equal to 5. Okay. Now, we can do this the same way we did the first question, or we can harness the power of technology and use this command, 1 minus p hyper. And it's important because the parameters are a little bit different for this problem. So if we want 4 and above, p hyper is going to give us everything to the left, like the p version of these commands always do. So we're going to want 3 and below. Okay, so we're asking for 3. And the other parameters, again, are a little bit different. We've got our number of successes next in the population, then number of failures in the population instead of giving the large, like big N. And finally, the sample size. And this will give us 0.3134. Okay. And then last, what is the probability that at most 2 people saw the super blue blood moon, so this is the probability that x is less than or equal to 2, which we can just kind of put directly into our p-hyper command. And again, 2, 15, 10, and 5. So these last 3 parameters don't change. Our 2 is just whatever the question may ask us for. And that gets us 0.3012. Okay. So that's it for the hypergeometric distribution. The last special discrete distribution that we're going to cover is the Poisson distribution. This is a count of the number of times a specific event occurs during a given interval. In general, you're looking for events to be determined or to be described as a rate. Okay, so in this instance, we're dealing with children per day in a hospital. Okay, so anytime you see something like that, you should be tipped off that you're dealing with Poisson. The other thing is, if you take a look at these formulas up here, you don't usually get very much information when you do a Poisson distribution question. The mean is equal to this term lambda, which is also equal to the variance. So they can give you this in any number of ways. They can report a variance to you, they can report a mean to you, or they can explicitly give you lambda. It's all the same number. And you really only get one number plus, the event that they're going to try and ask you questions about. So when you feel like you have very little information to go off of, it's usually a good idea to use the Poisson distribution. That being said, many questions like this one will throw in additional information to try and confuse you. So in 5.15 here, 50 here, amusement park rides are great family fun, but in 2016, more than 30,000 injuries were associated with amusement attractions nationwide. According to a recent study, on average, 12 children are treated in a hospital ER every day as a result of an injury from an amusement park ride. Suppose a day is selected at random. So here we see we've got our 12 children per day average, which is also our lambda and also our variance. So they could have said that the variance is 12 children per day, and they would have given us just as much information. So be careful. In addition, they've also thrown out this number, which is useless to us, but it makes you kind of think, like, should I be dividing 12 by 30,000 or something like that to get a probability? So be very careful, because this is a common type of question where they will inject information to confuse you. Okay, so just beware of that. A, what is the probability that no children will be treated in an ER as a result of an injury from an amusement park ride? So we can just plug our values into the formula here. And we've got e to the power of minus 12, because our mu is 12, which means our lambda is 12 as well, times 12 to the power of 0 divided by 0 factorial. Now, 12 to the power of 0 and 0 factorial are both 1, so we can really just cross those out, and we get this value. A very small value. If on average 12 children are treated every day, it's pretty rare to go without a day without treating a child as a result of an amusement park ride, which is unfortunate. B, what is the probability that at most 15 children will be treated in an ER as a result of an injury from an amusement park ride? Now, this is a question that we can do by hand. We could calculate, 0, 1, 2, all the way through to 15, and sum them up, and that would be a lot of work to do. But instead, we can also use our command in R, p+, and put in our parameters here. We want 15 or less, at most 15, and our lambda, which is 12, and that gives us a value of 0.8444. Okay. The last one, which is kind of similar to the final question they've been doing for each of these, suppose that 20 children are treated in an ER as a result of an injury on an amusement park ride. Is there evidence to suggest that the claim of 12 every day is wrong? So because 20 is higher than 12, we're going to go for the probability that x is greater than or equal to 20. And in order to do that, we're going to do 1 minus this command here. We're going to find the flip side of 19 and below, should give us 20 and above. And we find that this is equal to 0.0213. This is less than 0.05, and we say that this is very unlikely. Okay, so this 12 everyday claim, if we sampled this single day of 20, that wouldn't really be pointing to the fact that pointing to the truth being that 12 children every day is the average. Okay, so something might be a little bit incorrect. This might be an ER that's maybe particularly close to an amusement ride, something along those lines. Okay. Okay, that's it for this tutorial. I hope that it was helpful. It definitely ran a little bit longer than I wanted it to, but hopefully there's enough information that makes kind of worth your while. I hope it covered these commands well enough. I'm going to be making the tutorial for the next one, so if you have any feedback, please let me know, and I'll try to incorporate it for the next tutorial. Thank you very much.